Uh, Hello, everyone, and welcome to this webinar. I'm so glad to introduce Professor Wang. Professor Wang is currently an associate professor with the Center of Reliable Power Electronics, or Aalborg University, Denmark. And Dr. Wang received his PhD degree from the City University of Hong Kong in 2012, and the BE degree from Huai Wang University of Science and Technology, Wuhan, China, in 2007. He was a visiting scientist with the ETH Zurich, Switzerland, from August to September in 2014, and with MIT, Cambridge, USA, from September to November 2013. He was with the ABB Cambridge Research Center, Switzerland, in 2009. He served the guest editor-in-chief of IEEE JSP special issue on power electronics for energy-efficient buildings, and the associate editor of IEEE transactions on power electronics. Dr. Wang's research interests include the reliability of power electronic components and systems, multi-physics modeling, the virtual prototyping in power electronics, life cycle performance optimization of power electronic systems, DC-DC converters and inverters for motor drive, PV, and wind power applications. Today, Professor Wang is going to give a webinar on the towards reliable power electronics. Now, welcome, Professor Wang.
Thank you, Dr. Yang, for a kind introduction. Good day, power electronic colleagues. Welcome to this IEEE Professionals webinar. This is Huai from the Center of Reliable Power Electronics, Aalborg University, Denmark. Actually, I've been thinking for a while about the topic that will be given today. After receiving the invitation for this webinar, there were a bunch of specific research topics in my mind. Then one day, it occurred to me that why not taking this opportunity to discuss with us about some future trends in the area of power electronics, instead of digging into a very specific research topic. As one of the researchers graduated in the last decade, like most of you, I frequently think about what will be going on for power electronics in the next 20 years or more. There are many power electronics gurus have shed the light in the past 4 generations. So in this webinar, I would like firstly to share my perspectives about the historic development and some future of the trends in power electronics. Then secondly, one of the future trends towards more reliable power electronics will be discussed with us, which is the main research focus of myself and the team in Aalborg University in the last 4 years. That's why I choose this topic in title of this towards reliable power electronics. Of course, I would be very much like to also hear from your views after these webinars. So here is actually shows my career development to the area of reliable power electronics. I did a PhD in Hong Kong after I graduated, and I came to Denmark in 2012 and joined the newly established center that is called Center of Reliable Power Electronics. There are a series of fantastic research topics which are challenging and also been very interesting to me. Another motivation factor that is during my PhD study, I started to look at the reliability issues of capacitors and try to find some way from circuit design aspect to overcome the issue. This is the starting point that made me interested in the reliability of power electronic systems, which in my perspective is one of the important trends in power electronics research that will be discussed in a few slides later. So let's first look at the realization of power electronics converters. We are all familiar with that a power electronic converter is to convert and control electrical energy at circuit level, including maybe switches and passive components, to regulate the voltage, current, or frequency, the electrical power flow is controlled and regulated by varying the electrical impedance of one or more elements in the circuit network. Therefore, it requires some elements that are time-varying in either resistance, capacitance, or inductance. Actually, Dr. Wilson, in one of his papers in 2000, had given a very good discussion from this time-varying impedance perspective. In order for power converter to be as efficient as possible, this time-varying impedance between the source and nodes can be changed, should be changed actually as rapidly as possible between values that are orders of magnitude different. There could be three cases. The sketch in the left-hand side shows the behavior of the resistive switch. It's like the characteristics of a resistor that we are all familiar nowadays can change its first quantum value of resistance, RD, back and forth between high and low values. Similarly, the other two cases are capacitive switch and inductive switches shown here. For example, a typical separable reactor acts like inductive switch. When we look back since early 20th centuries, in the first 50 years or so, we can see that power electronics pioneers were trying to search for switches that can exhibit the required time-varying impedance characteristics, from the vacuum tube to the invention of the thyristor, the SCR, that is in 1957. After that, different types of power electronics semiconductor switches were introduced, from thyristor to power MOSFETs to IGBTs and to the wide bandgap devices, such as the GaN and the silicon devices. All these kind of devices have improved performance in terms of one or more aspects, like switching times, switching and conduction losses, power density, ruggedness, comfortability, cost, reliability, and so on. So the historic development of power electronics were heavily impacted by the development of power electronic semiconductors. It might be reasonable, so divided them into three development phases. The phase one is for the early 1900s to 1950s, the search for the suitable switches that can perform like a time-varying impedance. So this takes actually about 50 years. So the phase two covers the second 50 years, that is until the late 1950s to 2000s. A large number of circuit topologies during this period, and control and modeling methods of power electronics were proposed. So the switching frequency and efficiency of power electronics converters are increased, and more advanced gate driving strategies were applied. Besides analog control, digital controllers were more and more used in power electronic converters. This 50 years development has made many power electronics technologies reach a relatively mature stage. Since early 2000, we could see that power electronics was becoming more and more application-driven due to the specific requirements in different applications, and then there are much more extended scope in power electronics. And we could see that after this, we could see that research activities are increasing, like in packaging. This included both in device level, in component level, converter level, and system level. Thermal management, EMI and EMC reliability, modularization, and system of power electronic systems. So these are actually the past more than 100 years history evolution of power electronics. In terms of the physical quantities in power electronics, here's a nice figure that borrowed from Professor Connor from ETH. So it shows the evolution of the frequency, the size, power, voltage, and temperature ranges that is driven by a few types of applications shown here. That is the smart grid, energy harvesting, hybrid cars, and so on. So that is about the development history. So my personal view about the future of power electronics is quite optimistic. Even though technologies have their own cycle of life, it could be still a long way before power electronics become obsolete. This is by taking into consideration of the roles that power electronics play in the various electrical energy applications. This may be maybe one day, human beings find a better medium than electrical energy, but that in most possibility is not foreseen today. When we look at the future trends in power electronics, one of that could be software things like digital controllers, advanced algorithms, and information technology play more and more important role. That may fundamentally change the design methodologies of power electronic systems. While hardware becomes more standardized, they can be used to cater for different applications by just modifying the control algorithm. That is something like by installing different apps, more intelligence and auxiliary functions could be added by software solutions. Modular design will be another trend on also in power electronics. In terms of design process, further prototyping is expected to account much more during the design process. Due to the increasing labor cost and physical experimental prototypes, more importantly is because that the advancement of software tools enables the possible opportunities in connecting different physical domains, that is like electrical, thermal, mechanical, reliability, and so on, in power electronic simulations. Life cycle performance will become important instead of the time zero performance only. This is related to a bunch of aspects like the design itself, reliability, maintenance, and so on. Currently, the technologies for subsystem level packaging of power electronics converters, such as filters, intelligent power modules, links are available, which make the system level packaging more viable in the future. Another important trend and opportunities is on the passive components, that are magnetic components and capacitors. The technology development of them can be more power electronics driven. All of the above trends will be application driven, as discussed in the last slide. But we are now in the phase 3 of power electronics. There's limited few of them in those areas like the smart X, such as smart grid, smart city, and so on, and more electrical or all electrical aircraft in the vehicles. Besides this, biomedical will be another area that power electronics will play more important role. In information era like today, it is expected that more significantly power will be needed to be used to process the ever-increasing data. So efficiency and reliability of which very critical. So besides the research activities, you might feel that there's also a trend that to fundamentally change the way that people can do the research and education in power electronics. One of them is that the lab facilities might be able to be globally accessed due to this information technology, and also provide us a better collaborative way that we can better utilize a limited resource for education and research in power electronics. The figure shown here on the left-hand side is a lab from University of South Australia. So for this lab, any people all over the world, if they have an account, and then they can access this lab to collect the data to perform the experimental work in this lab. So that means these resources can be utilized, utilized by people all over the world. This is one aspect that may be a very interesting thing that we can consider in the future in both education and also research. And on the right-hand side is a kind of virtual laboratory. Actually, this is an example from in the chemical engineering, that the students of the course can perform the chemistry experiments virtually. So to see the phenomena, to see the things that related to the theoretical study, so that could be also a very cost-effective way for the education in power electronics. So it might give us some inspiration. So after discussing this historic development and also different trends, we could see that many times we have come to a word that is reliability. So as I said, this is my main focus in the last 4 years of research. So I would like to discuss a little bit more about on this topic. So why we need to towards more reliable power electronics? This is actually also because of the applications, the application-driven requirements. You could see that there are more emerging and critical applications like aircraft, offshore wind turbine, large PV plants, and some of the safety critical applications like the trains. But on the other hand side, they experience more and more harsh environments. So in this case, like the renewable energy application, we would like to reduce the cost of energy, and also we would like to, at the same time, there's a trend that we would like the power electronics part that has a higher power density. So this somehow a kind of compromised thing. So because of this application driver, so we need to achieve more reliable power electronic systems. The need some paradigm shift in research. We could see many times that in many reports or research papers that, especially in power electronics research papers, we could see that many reliability predictions are still based on the handbook calculations and are still based on some qualification testing to quantify the reliability of the products. So we need some paradigm shift in research, in reliability research. So this can be done. Of course, this can be done based on some methodologies that is already there in the reliability engineering, but also there is another area that is called microelectronics that could give us a lot of inspirations in the research in power electronics. So this is a motivation that goes the more reliable power electronics. So the next generation of, for example, the next generation of renewable energy system would have long operation hours under harsh environments. And the truth is that the fact is that the power electronic subsystems, one of the major failure sources is next generation product, which will be discussed a little bit later in the slides. And next generation products with return rate of part per million level and lifetime of 20 to 30 years. So increasing labor cost and maintenance and stringent cost constraints, all these impose great challenges to achieve these targets. So if we look at the cost of the poor quality or the cost of unreliability, we found that if we can identify the defect under the concept or design phase of the product, and then we can reduce the cost of unreliability by an order of magnitude. So, but if there is a defect that is not identified during the concept design or even the validation stage, when it goes to the field operation, so it will cost significantly more. So this is also the reason it's very important to consider the reliability performance as an important factor during the concept and design of power electronic systems. So here are shown, here shows some field experience in renewable energy applications. For example, here this slide shows the 5 years operation experience of a 3.5 megawatt PV plant in Arizona State, USA. So it's this data is published in 2008. So it showed that the PV inverters is responsible for around 37% of the failure events in the PV plants. Of course, there are also some other failure events, like that is from the PV panel, that is from the junction box or data acquisition system. And this 37% of the failure events induced by the PV inverters actually will introduce around 60% of the cost. So this cost includes like the maintenance cost, the repairing cost, but also include the cost that unavailability of the PV system, because during this repairable time, there will be no power generated from this PV. So this is an important part actually of the cost. Another example is on the field operation experience for wind turbines. So these are based on survey of almost 10 years operation of 350 onshore wind turbines in Germany, in UK, and in Denmark. So totally there are recorded of 35,000 downtime events. So the statistics shows us that power converters is responsible for 30% of the failure of all of these 35,000 downtime events. And these 30% downtime events of power converters is responsible for around 18% of the downtime. So as we know that normally these wind turbines have a power level of megawatts. So the downtime means there will be no power generated during this time, even there is a very good wind resource. So this will finally reduce the annual generation of the total energy. Also, that means it will increase the cost of energy. So these are the field experience. So let's look at the reliability challenge from industry. So this table actually is a result of a one-day meeting with different Danish companies. So it shows the past, present, and future reliability challenges in the industry. So in the past, the practice is that the customer expectation is that if one item or system is failed, and then we just replace it, and we take care about years of warranty. And the reliability target is in terms of the affordable returns, and the industry like do the reliability test and avoid the catastrophic failures. The main R&D tools is product operating test. So present in the current stage, the state of the art is that the customer expects low risk of failure and request for maintenance. Of course, the reliability target is the low return rates. And in some industry sectors, like in automotive operations, so automotive sector, they do like the robustness test and also try to do some hot test to improve the weakest components. And R&D tools, one of the important one is testing at the limits. That is like the hot test. So in the future, the customer may need the peace of mind. That means don't worry about the failure anymore, and they would like to see some predictive maintenance, require some predictive maintenance that can predict the wear out or type of failure of the components or systems, and then can reduce the unscheduled maintenance to finally to zero. The reliability target is more stringent. That is talking about part per million return rates, and the R&D tools like the design for reliability. It is an approach that tries to build in the reliability consideration from the starting point of the product design process, and also consider the emission profile balanced with the feed load. So there are a bunch of R&D key tools. Like one of them is that physics of failure, that is understanding the failure mechanisms besides, of course, like the reliability data, but we try to dig into the physics to understand the failure mechanisms and try to avoid it. And also the feed load, root cause. Another one, the multi-domain simulation. So try to simulate the electrical, thermal, mechanical, and humidity things into the of the system. So of course, it should be noted that the reliability, when we talk about the reliability here, is for most of the industry application. So there is a constraint cost. So that means to design high reliability power electronic system at constant cost is really a great challenge. Here shows some specific lifetime targets in power electronics applications. For example, the aircraft. automotive, industry motor drives, railway, and renewable energy like wind turbines and PV plants. So aircraft currently in typical lifetime target is a 100,000 hours flight operation. Automotive, I think most of us are familiar with that. And industry motor drives, it varies for different applications, of course, because there are different types of motors and applications. So like 5 to 20 years. Railways typically is 20 to 30 years of operation. That is, in terms of hours, that is like 70,000 hours to 110,000 hours. Wind turbines, most of the wind turbines nowadays are designed for 20 years of operation. That is around 120,000 hours. The PV plants nowadays are designed like 30 years, and it's equivalent to like 90,000 hours and 130,000 hours. So it should be noted that this is a lifetime target of the PV plants. Currently, actually, only a few of the PV inverters in the market can have this such kind of this number of lifetime. So if the lifetime of the PV inverter is like 5 or 10 years, and then in this case we need to change the PV inverters like 3 times or even 6 times during the life cycle of these PV plants. That will actually introduce additional investment during the operation of the PV plants. So according to this like field experience and industry expectations for the future reliability requirements and also the challenge we shown here, in the Center of Reliable Power Electronics at Aalborg University, we have trying to do some research in this multidisciplinary research area. So we have defined 3 major aspects of the reliability of power electronics. That is first the analytical physics, and the second, this is mainly the physics of failure and also the component physics, like the IGBT, like the capacitors, like the magnetic components, try to identify the root cause and also the major type of failures of those components. So this is a fundamental understanding. And then we go for the second aspect, that is design and verification. So that is included design for reliability approach, that implemented from the concept stage to design stage, and then for the robustness validation, this is related to the a series of accelerated testing and also robustness testing. And then go to the third aspect, that is when the products have been designed and have been released for the field operation. So there are still opportunities for us to improve the reliability or to achieve preventive maintenance. That is related to the intelligent control and also the condition monitoring. So we can, based on the operating condition, we can introduce some intelligence into the control. We can balance with the load. Also, we can monitor the healthy status of the critical components like the high power IGBT modules or the like DC capacitors or the filter capacitors. And then in this case, we know the expected end of life of those components, and then we can arrange the scheduled maintenance. So these are 3 major aspects of the power electronics reliability in our perspective. And then we also identify some paradigm shift that needed in the reliability research. So the first thing is that is from the components to failure mechanism, because we would like to, based on this physics of failure approach. So for single component like power IGBT modules, so there are a number of failure mechanisms. So each type of failure mechanism will affected by stressors like temperature, like humidity, to a different degree. So we would like to differentiate the failure mechanism and to build up the lifetime models for different failure mechanisms. Instead of those like in now in most of the handbooks, we give a single lifetime model for the components. And then we would like to go through from the constant failure rate to variable failure rate, because this is especially true for many electronic components, because the wear out of those electronic components starts from the beginning. So that means the failure rate of many electronic components actually is not constant. So the assumption of the constant failure rate will give us invalid results. The third aspect is that from reliability prediction to robustity validation. So reliability prediction gives us a number like the lifetime information, like the reliability, the probability to fail. But robustness validation has more comprehensive scope, that is to check whether this product design can fulfill or the insensitivity to different parameters. So the fourth point I would like to point out is that, as I said, in microelectronics, there is actually many good methodologies and tools have been implemented there. That is, since like 1990s, the failure approach has been well applied in the microelectronics part. There would be many synergy between the microelectronics and power electronics, but also, of course, power electronics has its distinctive components and also other issues, opportunities. So that's why here we say from microelectronics to also power electronics. So here is the slide shown here. We show the design for reliability process in power electronics. So we consider on the right-hand side, here is the 5 different stages of the product design. That is from the concept stage to design, validation, production, and release. So here we mainly focus on the design stage. That is, we divide it into 4 steps. That is, the first step is analysis, and then the initial design, and then we go to verification, optimized design. In the analysis, like we do circuit and system stress and strain analysis. That is, stress is like loading condition, the loading stress, and the strain is inherent capability of the device. And also, there is one term that is the failure mode effect analysis and critical component list and the critical failure mechanisms. So this is some terms from the reliability engineering. And in this analysis stage, because there are always variations during the manufacturing process, so it's good to include the consideration of the variational parameters in this analysis stage. And then we go to the multi-domain simulations, and also in power electronics, we have the opportunity to doing the fault-tolerant design, and also we can do the load management design, further prototyping, and initial reliability and durability analysis. So I will not go into the detail of each step. Actually, each of the items could be 1 or 2 PhD research topics. And then we go for the verifications. That is mainly the prototype building and also different kind of testing. And final stage would be the optimization stage, because the reliability is important, but it's still only one of the performance factors. We need to consider also other performance factors for the specific application. So we need to optimize always some optimization and trade-off design. But there are many items can be seen here that included in the design process. But basically, we can emphasize 6 aspects. That is the first thing that is more mission profile based design. So what is a mission profile? Mission profile is all of the operation environmental stress conditions of the power electronic system during the whole service life. So try to optimize the mission, the life cycle performance, instead of only like a full load condition or half load condition. So the second one is that the reliability analysis here are trying to be based on the physical failure approach, and also the multi-physics-based simulation analysis will play an important role in this analysis, because this is related to multi-domain and electrical domain and also thermal domain and mechanical domain, because there are some mechanical strength, and this will induce the reliability issue. And then it includes two kinds of testing. One is a quantitative testing. That is, the purpose of those testing is try to find the weakest point of components. That is not for the purpose of deriving some lifetime model or just quickly find the weakest point. And the second type of testing, that is quantitative testing, that is try to get some reliability information and data. So those data would help us to build up reliability models. And then multi-objective optimization would be very important to have a compromised design between the reliability and also other performance factors. So the main purpose of this seminar is to introduce the scope of power electronics reliability and also the general design process. But here I also would like to add some examples and research activities that have been done in Apple University. So the first example I would like to share is a power cycling test. So this kind of, because the IGBT modules has three important failure mechanisms in the packaging network. So all of these three kind of failure mechanisms were affected by the thermal cycling, that is the variation of the temperature. So in this testing setup, we test the 1.7 kilovolt 1000 N IGBT modules with a real PWM switching currents, and also we implemented a method to online monitoring the unstable voltage, because the unstable voltage with a careful calibration is a good indicator for the junction temperature of IGBT. So during the testing, we monitored the junction temperature of IGBT, and then we stress them at accelerated condition, and then for the long-term testing. So here is some results show the testing results. So we test 4 IGBT modules, that is after 2.5 millicycles, 3.5 millicycles, and so on to 5.1 millicycles. So after each testing, based on the increase of the unstable voltage, we can estimate the wear-out conditions of IGBT. Besides this, the tested samples can also be used to perform the failure analysis for microscopic investigations. So another example is for the power cycling testing for low power IGBT modules. That is for 600 volt 30 amp low power IGBT modules, that is for motor drive application. So 6 switches are integrated in the power module. So in this testing, actually we're trying to investigate the cycling period impact on the lifetime of IGBT modules. So another kind of testing that we perform is for the because beside the IGBT modules, the capacitors is another type of reliability critical components. So we also do some accelerated testing of capacitors. So here our purpose is trying to identify the humidity impact on the film capacitors for DC-link applications. So here shows a capacitor testing system that is included 3 major parts. That is, of course, the first one is the diametric chamber, and then we have some electrical source. That this kind of electrical source that is called the ripple current tester. So it simulates the DC-link voltage, like 1000 volts, and then plus some ripple current plus some AC voltage. So try to simulate the real operation conditions of the DC-link capacitors, but at an accelerated temperature or humidity level. So here shows some results of the capacitance degradation under 3 different humidity levels at 85 degrees. The reason we did this test is that because from the capacitor, film capacitor data show, the lifetime shown there is under the under dry condition and rated voltage and rated ripple current. So, but that is normally larger than 100,000 hours. So here, if we tested them, operate them in high humidity conditions, it can be found that the lifetime, the end of lifetime could be significantly reduced. For example, here we can see that the capacitors under the 85% humidity level, the lifetime, if we consider 5% drop in the capacitance as criteria, and then it's only between some 1,000 hours and 1.5 thousand hours. And then if we look at the 55% humidity level, and then the lifetime is around 2.5 thousand hours, and between 2.5 thousand hours and 3,000 hours. So another example is that IGBT lifetime prediction. So here shows application of 2.3 backward power converters, and then we consider emission profile of the wind speed, but also actually here is also the we also consider the ambient temperature conditions, and then we monitor the junction temperature of IGBTs, and based on some algorithmically process this temperature information, and then according to the lifetime model of these IGBTs, and then we can predict the lifetime of the IGBT in different failure locations, that is the solder joints, IGBT chip, and wire bonds, because these three locations are corresponding to three different failure mechanisms, and they have different lifetime models. Okay, here are just a very few examples that I presented here. Actually, there are many more research activities that can be found in the COP website. That is linked here. Okay, up to now, I would like to summarize this webinar. So we mainly have two parts. The first part, we have recap the development history in the past 100 years of power electronics. We have divided them into three phases, and then the current phase is that we could see that power electronics are becoming more and more application driven. So all the future trends will also be driven by the by different emerging applications. And then the second part, we have discussed a little more detail about more reliable power electronics that is related to the research activities in the multidisciplinary areas, including the power electronics, reliability engineering, and also the component physics. So thank you all for your attention, and I would very much like to have some questions from your side, but also I would very much like to hear your views about these discussions. Thank you very much.